Hello, everyone. Today, I'll introduce EventUPS, a new framework for performing uncalibrated photometric stereo using an event camera. At its core, photometric stereo asks a simple question. How can we infer 3D shape from the way an object reflects light? By capturing an object's changing appearance under different illumination, we can recover a highly detailed normal map, revealing its intricate geometry. It's a powerful technique, but it comes with a major catch. Traditional methods either require precise, tedious lighting calibration, or if the lighting is unknown, they demand massive amounts of data. This data requirement is a critical bottleneck for bringing high-fidelity 3D capture outside the lab and onto mobile platforms. Let's start with our final result. On the left is a reconstruction from a leading traditional method, which required 56 frames, each with 3 bracketed exposures to produce. On the right is our result. It's cleaner and more detailed, and it was generated from a stream of events that amounts to less than 5% of the data. This is the result of a fundamentally new approach, built for a new kind of sensor, event camera. Unlike a traditional camera that captures redundant frames at a fixed rate, an event camera is bio-inspired. It asynchronously reports only when and where brightness changes. This makes it incredibly fast, data efficient, and immune to motion blur, as this video shows. So, can we simply combine the detail of photometric stereo with the efficiency of an event camera? The answer is no, because there's a fundamental mismatch between the two paradigms. First, frame-based methods need absolute intensity to handle ambient light, often by subtracting a dark frame. Event cameras only provide relative logarithmic changes. Second, they rely on synchronous, dense frames to build constraints. Events are inherently asynchronous and sparse. And critically, resolving the classic mathematical ambiguity often relies on priors about the surface color, or albedo. The event generation process, however, is albedo invariant. We couldn't adapt old algorithms. Faced with this challenge, we developed EventUPS. We take a portable lighting rig with a known 3D shape and move it freely around an object. The event camera captures a sparse stream of brightness changes, and from this, our algorithm jointly recovers both the detailed surface normal map and the time-varying light trajectory. The key is to stop treating events as a poor substitute for an image. Instead, we recognize that the physics of event generation provides something powerful, a direct geometric constraint. Each individual event constrains the true surface normal to lie on a specific plane in a higher dimensional space. With enough events, these planes intersect, pinning down the precise 3D orientation. This insight allows us to tackle the first major challenge, ambient light. Starting with the Lambertian reflection model and the event trigger model, we derive a single linear equation. Critically, we don't try to remove the unknown ambient light and albedo. Instead, we algebraically group them into a single unknown ratio. This turns them from a problem to be eliminated into just another variable to be solved for. But this constraint links normals to lighting at different asynchronous moments. To bridge these gaps in time, we model the unknown lighting path as a continuous B-spline curve. This creates a shared temporal backbone that connects every sparse event into a single, globally consistent system. Finally, to solve the inherent ambiguity in the uncalibrated problem, we replace assumptions about the surface with a mild assumption about the light source. We use a lighting rig with a known 3D shape, but its global pose is completely unknown. We proved that this geometric prior is sufficient to resolve the generalized bas-relief ambiguity down to the classic convex-concave case. Our results validate this framework. The graph shows that EventUPS achieves superior accuracy to the non-learning baseline, PF14, while being over 20 times more data efficient. And it works robustly on real data captured with our custom rigs, successfully recovering both the detailed geometry of various objects and the uncalibrated light paths. In conclusion, EventUPS provides the first framework for high-quality, uncalibrated photometric stereo on an event camera. We turn the sensor's unique properties into strengths, achieving high-fidelity 3D shape with less than 5% of the data. This opens the door for low-power, low-latency 3D capture in uncontrolled environments, a critical capability for the future of robotics and augmented reality.